In this presentation, I'll be explaining few problems on star type connection as well as delta type connections. Now let us see problems on star connected loads. Problem 1. A star connected three-phase load has a resistance of 12 ohms and inductive reactance of 16 ohms in each branch. A line-to-line voltage of 415 volt is applied across it. Find the line current, phase voltage, power factor and power consumed. So this is the circuit diagram. It's a star connected system, resistance 12 ohms, inductive reactance 16 ohms, line voltage equal to 415 volt, and you're asked to find out line current, what is the line current, and what is the phase voltage, the phase voltage between phase and neutral, and the power factor and power consumed. Now let us see first the phase voltage. Line voltage has been given as 415 volt, and the relation of between the phase and line voltage in a star connected system, phase voltage equal to line voltage divided by root 3, or this voltage is equal to line voltage divided by root 3. Therefore 415 divided by root 3, that is equal to 239.6 volt. That is the phase voltage. And next you will have to find out what is the impedance of this one. Then we can find out what is the phase current, then the same as the line current. Therefore first phase voltage is calculated. Now let us see what is the impedance of this one. Impedance means Z, which is equal to square root of R square plus XL square. Square root of R square plus XL square. This is the impedance triangle. R inductive reactance. This is the impedance. Root of R square plus XL square is the impedance, and which is equal to square root of 12 square plus 16 square equal to 20 ohms. Therefore the impedance equal to 20 ohm, and this phase voltage is calculated is 239.6. Then you can calculate what is the phase current. Phase current equal to phase voltage divided by this impedance. Phase voltage divided by impedance, or that you will be getting, it is equal to 11.98 amps. Therefore this current equal to 11.98 amps. That is phase current. Phase current is same as the line current. In a star connected system, line current is same as the phase current. Therefore this is the phase current 11.98 amperes, same as the line current. Line current equal to 11.98 amperes. Therefore we found out line current, phase voltage and power factor. Power factor you can find out, this is the impedance triangle. Power factor equal to cos phi equal to R by Z. R equal to 12 ohms and Z is equal to 20. Therefore 12 divided by 20, R by Z, which is equal to 0.6. Therefore the power factor equal to 0.6. Now what is the power consumed? The active power or power consumed, P equal to root of VLIL, root 3 VLIL cos phi. Root 3 VLIL cos phi is the power consumed by the load for three-phase load. For root 3 into VL is equal to 415 into IL equal to 11.98 and into cos phi equal to 0.6. Then you will be getting P equal to 5166.7 watts. Therefore that is the power consumed by the three-phase star connected load. Now let us see another problem on delta connected load. A three-phase delta connected motor has a specification of 400 volt, 50 hertz, 5 amperes, 0.8 pf lagging. What is the power consumed by the motor? And also calculate the reactive power requirement of the motor. Therefore, first the line voltage is given as 400 volt, VL equal to 400 volt, and the line current is given as 5 amperes, and the power factor is given as 0.8 lagging. And here the power consumed, as the equation you know that P equal to root 3 VL IL cos phi. Therefore root 3 VL IL is given, it is equal to line current is given as as specified for 5 ampere. Therefore root 3 400 into 5 into 0.8 or 2.77 kilowatt is the real power or active power consumed. by the motor at a power factor of 0.8 lagging. And the second part is that what is the reactive power requirement. Now to find out the reactive power requirement, it is equal to root 3 VLIL sin phi. Root 3 VLIL sin phi. Sin phi to find out, the sin phi equal to sine of cos inverse 0.8, or that's equal to 0.6. For sin phi equal to 0.6, substituting this equation, the reactive power requirement of the motor equal to root 3 into 400 volt into 5 ampere into sine phi 0.6 equal to 2.09 kilo watt, reactive volt amperes, kilo reactive volt, kVAR. That is the reactive power requirement of the motor, and this is the real power consumed by the motor. Now let us see another problem, star connected circuit. Problem 3. A balanced star connected load is 8. It's actually 8 plus J6 ohms. Actually it is 8 ohms plus J6 ohms per phase. Balanced star connected load of 8 plus J6 ohms per phase is connected in a 3-phase 400 volt supply. Find the line current, power factor, active power, reactive power, and apparent power. Therefore, this is a star connected load 8 J6. That is here 8 ohm the resistance, and inductive reactance equal to 6 ohms. Therefore, this is a line voltage is 400 volt, VL equal to 400 volt, and then first thing you have to calculate what is the phase voltage. Phase voltage equal to, in a star connected system, phase voltage equal to line voltage divided by root 3. Therefore, phase voltage is given by 400 divided by root 3, 231 volt. This voltage. Next, you have to calculate what is the impedance per phase. That is, what is the impedance of this one. That is given by Z equal to root of R square plus XL square. Therefore, that is equal to root of R square plus XL square, or root of 8 square plus 6 square, or is equal to 10 ohms. Therefore, the impedance of this part is equal to 10 ohms, and this voltage equal to 231 volts. Then you can calculate what is the phase current. Phase current is same as the line current. In a star connected, line current is same as phase current. Therefore, the phase current is given by phase voltage divided by the impedance, which is equal to 231 divided by 10, or 23.1 ampere. That is the line current. Therefore, for source current, that is phase current, which is same as the line current. IL equal to 23.1 ampere. Next, let power factor. Power factor is given by, as we have seen previously, power factor is equal to, from the impedance triangle, cos phi equal to R by Z. Cos phi equal to R by Z. R equal to 8 ohm and Z equal to 10 ohm. Therefore, it is equal to 8 by 10, which is equal to 0.8. Power factor equal to 0.8. Then active power equation is root 3 VLIL cos phi. Root 3 into 400. That is the voltage, line voltage, into line current is same as phase current, which is equal to 23.1 into 0.8. That is 12.8 kilowatt is the real power or active power consumed by the 3-phase star connected load. And sin phi can be calculated, cosine of cos inverse 0.8, which is equal to 0.6. Therefore, the reactive power is given by root 3 VLIL sin phi, which is equal to root 3 into 400 into 23.1 into 0.6 equal to 9.6 kVAR, or reactive volt amperes. Kilo reactive volt amperes, kVAR. And next one is the apparent power. Apparent power can be found out by, this is the power triangle. This is the active power. This is the reactive power. This is the apparent power. S, this is Q, and this is P. Therefore, S equal to square root of P square plus Q square, which is equal to 12.8 square plus 9.8 square, which is equal to 16 kVA. Therefore, 16 kilovolt ampere is the apparent power. Now let us see another problem on delta connected load. Delta connected load has been shown here. A delta connected load of 12 plus J, that is again that much ohms it is. A delta connected load of 12 plus J 16 ohm per phase is connected to a 3-phase 400 volt 50 hertz supply. Find the line current, phase current, power factor, and active power. The load is a delta connected, and 12 ohm resistance, 16 ohm inductive reactance, so delta connected one. And you are asked to find out what is this current, line current, and of course the power factor and active power, phase current and power factor and active. For that one, first you have to find out what is the phase current. To find out the phase current, this is the phase voltage is same as the line voltage. In a delta connected system, this is called the line voltage, which is same as the phase voltage. Therefore, phase voltage equal to same as line voltage, which is equal to 400 volts. Now the impedance per phase, or this impedance per phase equal to, this is a 12 ohm resistance and 16 ohm inductive reactance. Therefore, the impedance is given by square root of 12 square plus 16 square is equal to 20 ohms. Therefore, the impedance of this one equal to 20 ohms, and this voltage is equal to 400 volts. Per phase current is equal to what is the voltage across this one into divided by the impedance. For 400 divided by 20 or 20 amperes. For the per phase current equal to 20 amperes. Therefore, and again in a delta connected, the relation between the line current and phase current equal to line current equal to root 3 times phase current. Therefore, this current phase current is calculated 20 amperes. Therefore, the line current equal to root 3 times phase current, which is equal to 34.64 amperes. Therefore, the line current has been calculated. Then next one, phase current also you can be calculated. Next, power factor. Power factor, as we have already seen, power factor from the impedance triangle, power factor angle cos phi, this is a phi, cos phi equal to power factor equal to R by Z. R equal to 12 ohms and Z equal to 20, or 12 divided by 20, which is equal to 0.6. So the power factor equal to 0.6. Again, active power, what is the power consumed by the the delta type load, that is equal to root 3 VLIL cos phi. The root 3 VL line voltage is 400 volt, which is the same as phase voltage. Root 3 400 into IL. IL equal to 34.64 into cos phi. Cos phi equal to 0.6. 0.6, it will begin 14.4 kilowatt. This is the active power consumed by the delta connected load. Let us see another problem on delta connected load, in which a three-phase delta connected balanced load connected to a three-phase 400 volt 50 hertz supply draws a 17.32 amperes. This current is equal to 17.32 amperes at a power factor of 0.8 lagging. Each phase has a resistor and inductor connected in series. A resistor and inductor is connected in series. Find the resistance and reactance and the inductance per phase. What is the resistance and what is the reactance, or what is the inductance value of this one? That is, to calculate that one, first in this delta connected load, as we know, phase voltage is same as the, line voltage is same as the phase voltage. Therefore, the phase voltage is same, which is equal to 400 volts. Now, line current is given as 17.32 amperes. The relation between line current and phase current is that line current equal to root 3 times phase current. Therefore, phase current equal to line current divided by root 3. That is equal to 17.32 divided by root 3, or 10 ampere is the phase current. Therefore, the phase current is calculated. Already phase voltage is not. Then you can calculate what is the impedance, that one. So for this voltage, phase voltage divided by the current, that is phase voltage divided by current, that is equal to 40 ohms. Therefore, the impedance is equal to 40 ohms. Which is V phase divided by I phase, that is the per phase impedance. The impedance of per phase equal to 400 divided by 10, 40 ohms. Then you have to find out what is the power factor is given. No, power factor equal to 0.8. Power factor equal to 0.8, as we know that power factor equal to R by Z. Therefore, R by Z equal to 0.8, Z equal to 40 ohms. Then from this equation you can find out R equal to 0.8 into Z, or 0.8 into 40, 32 ohms. Therefore, the resistance equal to 32 ohms. Then reactance equal to root of Z square minus R square. Z equal to 40 ohms, or root of 40 square minus R square equal to 32 square, or 24 ohms. Therefore, that is the inductive reactance XL. Therefore, you got what is R and what is XL. Then finally you are asked to find out inductance per phase. What is the inductance? XL is given by 2 pi f into L, or L equal to XL divided by 2 pi f, or 24 divided by 2 into pi into 50, or which is equal to 0.0764 Henry, or 76.4 millihenry. Therefore, that is the inductance. Therefore, inductance XL divided by 2 pi f, which is equal to 24 divided by 2 into pi into 50, which is equal to 0.076 Henry or 76.4 millihenry. Now next problem, problem number 6, problem on a star connected circuit. A 3 coils having an impedance 4 plus J3 ohms, 4 ohms resistance, inductive reactance 3 ohms. They are connected in star and delta across a 400 volt 50 hertz 3-phase supply. Calculate the line current and power in each case. When it is delta, what is the line current and what is the power consumed? And when it's similarly when it is star, what is the current and what is the power consumed? Now let us see first star connected case. Suppose this is a star connected load. Each branch it is 4 plus J3. For the 4 ohm resistance, inductive reactance equal to 3 ohms. And here the supply voltage equal to 400 volts. If you know the supply voltage equal to 400 volts, the phase voltage is given by, in a star connected system, phase voltage equal to line voltage divided by root 3. For 400 divided by root 3, 231 volt is the phase voltage. That is the case in star connected case. I think we'll first, it is explained as a delta here. Delta is explained in this one. In delta connection, as we have seen, it is equal to, now let us calculate first star connection. Star connection, of course, the phase voltage have to be calculated, in which line voltage equal to 400 volts. Therefore, phase voltage equal to line voltage divided by root 3, VL divided by root 3, 231 volt is the phase voltage, and impedance equal to 4 plus J3, that is 4 ohms, and this is equal to 3 ohms, or 4 plus J3. Therefore, impedance equal to root of R square plus XL square, which is equal to 5 ohm. 4 square plus, that is root of R square plus X square, that is the impedance 5 ohms. Therefore, this per phase impedance equal to 5 ohm and phase voltage equal to 231 volt. Then you can calculate what is the phase current, which is same as the line current. Therefore, I phase equal to V phase divided by Z, 231 divided by 5, 46.2 amperes. That same in the star connection, the phase current is same as the line current. Therefore, line current equal to 46.2 amperes. Next, you have to calculate what is the power factor. Power factor is given by cos phi equal to R by Z. R equal to 4 ohms, Z equal to 5 ohms. Therefore, 4 by 5, 0.8. Then the active power is given by P equal to root 3 VLIL cos phi, root 3 into line voltage equal to 400 volts, root 3 into 400 into line current equal to 46.2 amperes into the power factor equal to 0.8, which is equal to 25.6 kilowatt. Therefore, the power consumed by the three-phase load is equal to 25.6 kilowatt, and the line current is given by, which is equal to same as phase current, which is equal to 46.2 amperes in the case of a star connected load. Now coming to the same branches, they are connected in delta configuration, 4 ohms and 3 ohms reactance, inductive reactance 3 ohms, 4 ohms. Again, same supply, 400 volts is applied. Now, what is the power consumed and what is the line current? Therefore, here, in order to find out the line current, you have to first calculate what is the phase current. Phase current is given by, phase voltage is same as the line voltage. For phase voltage equal to 400 volts. Now, for the phase current is given by 400 divided by the impedance equal to 5. That is the phase current equal to 80 amperes. For the phase current equal to 80 amperes. Therefore, in a delta configuration, line current equal to root 3 times phase current. Therefore, root 3 times 80, root 3 times phase current IF, or root 3 into 80, or 138.56. For the line current in delta is equal to 138.56. Next, you are asked to find out what is the power consumed. Power factor is again, it is equal to 0.8, same root of, it is equal to, cos phi equal to R by Z, 4 divided by 5, it is equal to 0.5. Now, active power is given by root 3 VL IL cos phi. VL equal to 400 volts. IL is calculated, it is equal to, it is I phase IL equal to 138.56 and power factor equal to 0.8 or 76.8 kilowatt. Therefore, when it is connected into a delta configuration, now the power is increased to 76.8 kilowatt, and the line current is same as, line current is calculated as root 3 times phase current, which is equal to 138.56 amperes. Line current as well as the power consumed increase when it is connected to the delta configuration. This is the impedance triangle. There's another problem on a delta connection load, that is a three-phase delta connected balanced load connected to a three-phase 400 volts, 50 hertz supply, draws 15 amperes. The line, this is the 15 amperes the line current at 0.7 pf per factor lagging, and each phase has a resistance and inductance connected in series. Find the resistance, reactance and inductance per phase. Therefore, to find out that one, the line phase voltage is or line voltage is given as 400 volts, and the line current is also given. So the line voltage equal to 400 volt, which is same as the phase voltage. Then line current is given as 15 amperes. Line current is given as 15 amperes. Now line current and phase current, they are related in a delta configuration by phase current equal to line current divided by root 3, or line current equal to root 3 times phase current. Now to calculate the phase current, the current flowing through each phase, which is equal to line current divided by root 3, 15 divided by root 3, 8.66 amperes. So this current equal to 8.66 amperes, and this voltage is equal to 400 volts. Then you can find out what is the impedance per phase. That is this voltage divided by this current, which is equal to 400 divided by 8.6, which is equal to 46.19 ohms. So the impedance of each per phase impedance equal to 46.19 ohms. Next, what is the power factor? Power factor is given as 0.87. Power factor definition is equal to R by Z. Therefore, from this one, you can find out what is R. R equal to impedance is calculated 46.19. R by Z equal to cos phi. Cos phi is not. Therefore, R equal to Z into cos phi, or which is equal to cos phi 0.7 into Z, 0.7 into 46.19, which is equal to 32.33 ohms. Therefore, resistance equal to 32.33 ohms. Then you have to find out what is the inductive reactance XL. XL can be calculated square root of Z square minus R square. Square root of Z square minus R square, which is equal to 46.19 square minus 32.33 square, equal to 32.99 ohms. Therefore, this is the inductive reactance and this is the resistance. Then final part is that find out the inductance per phase. Inductance is given by XL equal to 2 pi F into L. Inductive reactance equal to 2 pi F into L, or L equal to XL divided by 2 pi F, or XL is, we have calculated 32.99 divided by 2 pi, 50 is the frequency, then it is equal to 0.1050 Henry or 105 millihenry. Therefore, that is the inductance of this one, and the resistance is equal to 32.33 ohms. Now let us see another problem on star connected circuit. Problem number 8. A balanced star connected load of, that is, load is connected to a three-phase 400 volt 50 hertz supply. Line current is 15 amperes. Power factor is 0.7 lagging. Calculate the total power taken by the load. If the load were reconnected in delta supplied from the three-phase supply, calculate the line current. This is the question. Therefore, first it's a star connected load. In that one, the line voltage is given as 400 volts and line current is given as 15 amperes. First stage is that first you have to find out what is the power consumed. Power consumed is equal to root 3 VL IL cos phi. P equal to root 3 VL IL cos phi. In that one, VL is given, IL is also given, but you have to find out what is the cos phi. Cos phi is also given, 0.7 lagging, that's also given. Therefore, the active power is equal to root 3 VL IL cos phi, or you will be getting 7274.6 watts. That is the active power. Now, next is you have to calculate the total power taken by the load. In star connected system, phase voltage is given by 231 volt, because phase voltage equal to line voltage divided by root 3, which is equal to 400 divided by root 3, which is equal to 231 volts. You know the line current equal to, it is given as 15 amperes. which is same as the phase current, and the phase voltage equal to 231 volts, then you can calculate what is the, of course, line voltage is the, line current is also given. And what is the impedance? What is the impedance is given by phase voltage divided by 231 divided by 15 amperes. That is the impedance per phase is given by 231 divided by 15, or 15.4 ohms is the impedance per phase. Now the same thing you are going to connect as a delta. The same thing you are connecting as a delta. In that case, on connecting to delta, V phase will be same as 400 volts, because this will be connecting in a delta. The per phase voltage will become same as the line voltage, which is equal to 400 volts. And then per phase current will become, what is this per phase voltage divided by what the impedance we calculated. That is 400 volts divided by the impedance 15.4 ohms, or that is equal to 25.97 amperes when it is connected in delta. And when it is connected in delta, line, that is, this is the phase current, and the line current is given by IL equal to root 3 times IF, or it is equal to root 3 times this one, 25.97 amperes, which is equal to root 3 into 25.97, or 44.98 amperes. Therefore, when this load is connected in delta, instead of 15 amperes from the line, it takes 44.98 amperes. Now let us see another problem in delta connected load. Problem number 9. A balanced delta connected load of 8 plus J6 ohms. Load of 8 plus J6 ohms per phase is connected to a 3-phase 400 volt 50 hertz supply. Find the line current, phase current, power factor and active power. Therefore, this is a delta connected load in which the per phase resistance is 8 ohm and inductive reactance equal to 6 ohm. Is a delta connect, and the phase voltage or line voltage both are same. That is given as, it is equal to 400 volts 50 hertz. Now you are asked to find out what is the phase current, what is the line current, and what is the power factor and active power. Now let us see first, to find out the phase current, impedance you have to calculate. What is the impedance of this one? Impedance is given by root of R square plus XL square. R square plus XL square, root of 8 square plus 6 square, which is equal to 10 ohm is the impedance. Impedance per phase. The voltage per phase is same as, line voltage, which is equal to 400. Therefore, the current per phase is given by 400 divided by the impedance per phase. 400 divided by 10, which is equal to 40 amperes, is the current per phase current. Now, if you find out the per phase current, the line current is given by root 3 times phase current. In a delta connected load, line current is equal to root 3 times phase current. Therefore, IL is calculated equal to root 3 times 40, which is equal to 69.28 amperes. Then power factor is given by, of course, from the impedance triangle, power factor is given by R by Z. R means 8 ohms and Z equal to, we calculate 10 ohms. For 8 by 10, which is equal to 0.8 is the power factor. For line current calculated, phase current calculated, power factor. Active power is given by root 3 VLIL cos phi. Root 3 into VL equal to 400 volts, IL equal to, it is equal to 69.28, which is equal to root 3 times 40, 69.28 amperes. IL into power factor equal to 0.8. Therefore, it is equal to 38,398.8 watts. That much watts, or 13.8398 kilowatt. Now one more problem on delta connected load. Problem number 10. The load in each branch of a delta connected balanced 3-phase circuit consists of an inductance of 20 millihenry in series with a resistance of 10 ohm. Line voltage is 400 volts and 50 hertz. Calculate the line current and total power in the circuit. What is the line current and the total power consumed by the load? Now, line voltage equal to 400 volts, which is same as the phase voltage, and the resistance R equal to 10 ohms, and inductance is given as 20 millihenry. From this one, you have to calculate what is the inductive reactance XL. XL is given by 2 pi F into L. 2 pi F, 50 hertz 50 into L, 20 millihenry, or we will be getting 6.28 ohms. Therefore, XL equal to 6.28 and R equal to 10 ohms. Then you can find out what is the impedance. Z equal to root of R square plus XL square, square root of 10 square plus 6.28 square, which is equal to 11.8 ohms. For the impedance per phase, which is equal to 11.8 ohms, and the resistance equal to 10 ohms. And once you know the impedance here, that phase current is given by, in a delta connected, phase current is equal to phase voltage divided by phase in impedance. Phase voltage is same as the line voltage. Therefore, phase voltage is same as voltage, that is 400 volts divided by impedance 11.8, which is equal to 33.9 amperes. Therefore, this current equal to 33.9 amperes. Then line current equal to root 3 times of this phase current. Root 3 into 33.9, or which is equal to 58.7 amperes. For the line current equal to 58.7 amperes. And the line voltage is equal to 400 volts. Therefore, the power equal to root 3 P VL IL cos phi. The power factor can be calculated. Power factor equal to R by Z, which is equal to resistance equal to 10 divided by Z, which is equal to 11.8. Actually, this is 11.8. Power factor equal to R by Z. R equal to 10 ohms and Z is equal to 11.8 ohms. Therefore, 10 divided by 11.8 or 0.85. Power factor equal to 0.85. Then the active power equal to root 3 VL IL cos phi. Root 3 into 400 into 58.7, that is the line current. That into power factor 0.85, which is power. Therefore, the real power or active power equal to 35.57 kilowatt.